Okay, welcome back everyone. Earlier in this lesson, in this chapter, we said that you could treat an extended object, a spherical mass distribution, as though the force of gravity acted at its center. So today, what we're going to try and figure out is why is that so? And this was a calculation that Newton actually did many years ago, and it's pretty sophisticated for back then. But here's a picture of the situation. We're going to start with a point mass that's outside of a spherical shell. And essentially, what we want to prove is that we can treat the force as coming from the center point O. Okay, so if we can prove that a spherical shell acts like this, that all of its mass m is concentrated at the center, then we can also extend this to a solid sphere. Okay, so a solid sphere like a planet would just be a series of shells. So then we can show that the force of gravity acts from the center of mass of one object to the center of mass of the other. Okay, so we're going to go ahead and prove this, and it's going to take a little bit of doing here. Okay, so the first thing we're going to do is get all set up here. Okay, so here's our setup. We have the spherical shell, and essentially what we want to prove, so this will get us there, is we want to prove that the potential energy between the big mass m and the little mass little m is going to be equal to negative g big M little m over r. And then we'll just use the fact that F is negative du dr to get back to force. And so if we can prove that this expression is true for u, then we're done. Okay? So the first thing that we do is we take this shell and we break it up into rings. And one of these rings is shown in this diagram. And this ring can therefore be thought of as a small amount of mass dm. Okay, so the ring has a mass of dm. Okay, so one thing that we can say is that the total mass of the shell will be m. Okay, so the shell will be this mass, big M. And so therefore, if we can integrate dm, that will give us big M. Now the other thing that we have to do is we actually have to break this ring up into small pieces. Okay, and we're going to say that a piece of a ring, or a chunk of the ring, is going to have mass of mi, a very small amount of mass. Okay, and so let's say that this small amount of mass is right here. Well, that didn't show up too well, so let's get a better color to show up. Okay, so right here, that's where our where our mi is going to be. Okay, and so what we can do is we can calculate the gravitational potential energy between that small mi and the point mass little m, and we can say that the potential energy from that is equal to negative g mi little m over s, and s is the distance from mi to m. Okay, and we can do a couple more things here. Okay, we can say that the area of the ring is equal to dA. Okay, and then we can say that the potential du from an entire ring is going to be negative g dm m over s, because all parts of the ring are at the same distance s from the point particle. Okay, so now we can go to sort of the meat of this, which is to say that dm over the entire mass of the shell is equal to dA over the entire area. So this means that dm is equal to the entire mass times dA over A. But now let's look at an expression for dA. And we have it on the screen here. Basically, dA is going to be the circumference of this ring, so 2 pi r sine phi. Okay, phi is this angle here, and r sine phi is the radius of the ring. So this represents the circumference, or the length to go around. And then the width of this is going to be r d phi. And so you can see that here, that is the width of a ring. Okay, so circumference times width is going to give me the area. Okay, so let's set this up. Okay, so dm is equal to m times 2 pi r squared, because of r and r, sine phi d phi, all over, okay, let's think about this. What's A, the total surface area of this shell? Well, it's just going to be 4 pi r squared. Okay, so what we can do is do some cancellation here, and those r squares cancel out. So this means that dm is equal to m sine phi d phi over 2. So that's dm. Okay, so that's a good start. It's a very good start. Okay? So the next thing that we want to do is we want to take this expression for dm and we want to plug it into du right here. So the last thing that I'll put on this slide is that du is going to be equal to negative g big M little m sine phi d phi over 2s. Okay, so the g, the m, and the s are here, here, and here, and everything else is dm. Okay, now one problem that we have is that we need to turn s into something else involving r and phi. Okay, so we're going to go to another slide here to have a little bit more space, and we can say, using Pythagorean Theorem, okay, that s squared is going to be equal to, let's just indicate this on our picture here, this distance squared plus that distance squared. Okay, so if you call that A and B, and the hypotenuse is C, so C squared is going to be A squared plus B squared, okay? But A is going to be the total distance from center to center, which we're going to call R, minus, let me draw it in kind of a blue here, minus this distance here, which is going to be R cosine phi. Okay, so it's going to be R minus R cosine phi. That's big R cosine phi. That'll be squared. And then B is just going to be R sine phi quantity squared. Okay, so we're going to expand this a little bit. S squared equals R squared minus 2 little r big R cosine phi plus r squared cosine squared phi plus r squared sine squared phi. And then you'll notice that right here, sine squared plus cosine squared is 1, so that's just going to turn into r squared. Okay, so we're going to have s squared is equal to r squared minus 2 little r big R cosine phi plus big R squared. Okay, so we're getting there. Now what we're going to do is we're going to differentiate each side. So we can write that 2s ds, okay, so s is going to be changing as we move around to different rings, so S is a variable. Little r is not a variable because it's just how far we are from little m to big O. Okay, so it's OP in other words. Okay, so r is actually equal to OP in that diagram, and that's not changing. So when we take the derivative of r squared, it's going to go away. The same thing with big R, okay, because big R is just the radius of this shell, and remember we're just doing one shell right now. So the only thing that's going to be changing is really the middle term, and the cosine of phi is going to be changing there. Okay, so the derivative of cosine is going to be negative sine, which will cancel with this negative to give us 2 little r, big R, sine phi d phi. Okay, and we can rearrange this a little bit. Okay, and we're going to rearrange this to be in this form. ds over 2 little r big R is equal to sine phi d phi all over 2s. Now why do we want to write it like this? Well, remember that last slide we said that du for a ring is negative g little m big M sine phi d phi all over 2s. And so all of this right here, sine phi d phi over 2s, is actually ds over 2r big R. Okay? So now we can write that du is equal to negative g big M little m ds over 2 little r big R. And so therefore, to calculate the potential of a shell, we must integrate the potential energy of a ring. So that's going to be equal to, well, let's think about this. This ring is going to start at the top, okay, which is going to be little r minus big R. And it's going to go to the bottom, which is little r plus big R. And we're going to be integrating negative g big M little m over 2 little r big R ds. Okay? Now, what's the great thing about this? Well, there's no dependence on s. Okay, so we can take out the negative g big M little m over 2 little r big R, and then the integral of ds is just s evaluated from r plus big R to r minus big R, which is equal to negative g big M little m over 2 little r big R times little r plus big R minus little r minus big R. Okay, and you're going to see that these little r's will cancel, and this is going to turn into 2 big R because of the pluses there. So u for a shell is equal to negative g big M little m times 2 big R over 2 little r big R. And this is amazing because the 2r cancels and the 2r cancels, so we get that u for a shell is equal to negative g times the mass of the shell times the mass of the point particle over the radius of the shell. And this is exactly what we set out to prove on our previous slide. We want to show that u is equal to negative g big M little m over r. And if that's the case, then we know that the force is basically g big M little m over r squared, which shows that the force of gravity is concentrated at the center of the shell. And then from here, it's a very easy calculation to add up all of the shells that would be in a sphere, and we're done. We have done what Newton did, which was to prove that all of the mass of a planet, a star, any spherically symmetric object is concentrated at the center, and therefore it can be treated as a point particle. So that's pretty cool. Okay, now what happens if the point mass is inside of the shell? Well, we're not going to do this. You can try this if you want, but the limits of integration just have to be changed. Okay, so if I have a point right here, then this is little r and this is big R, and we just have to change our limits of integration. So I'm not going to do that right now, but we get a very similar result. Okay, so in the next video, we're going to talk about how this result can be used, and we're going to talk about a very important concept, and that is Gauss's law.